If you haven't watched the Getting Started video, you may want to watch that video before you watch this video. You may also want to watch the cross-section video. In this video, I'll show you how to create infinite polygonal prism items. You might also call this 2D polygon modeling because it's equivalent to the sort of traditional 2D models that use polygons. The only difference is that FastGrav's prism items are embedded into FastGrav's 3D coordinate system. So they are more flexible if you're working with several transects of different orientations or several types of mass item. If you like, you can think of FastGrav's polygon prism items as a purely 2D modeling method. Just keep in mind that there is a 3D system underlying this 2D approach. Okay, I'm going to open up one of the examples that comes with FastGrav, and we'll use that to demonstrate polygon prisms. I'll use the basic prism example. Alright, so this project already has a polygon prism in it, as you can see in this cross section. You can see that the shape of this anomaly is sort of reflecting the lopsided shape of the polygon. Let's take a look at the polygon prism's properties. Similarly to a cylinder item, the polygon prism's position and orientation are defined by an axis point, x, y, and z, and an azimuth. The polygon prism item also has a list of vertices defined relative to the axis point that define the shape of the polygon. So each one of these x, z rows corresponds to one of these vertices. An important thing to remember is that these vertices are defined relative to the axis point, not in absolute coordinates in space. So, for instance, this row right here is saying that there is a vertex 2 meters to the left, -2, 2 meters to the left of the axis point, and 2 meters above the axis point. This relative definition of vertices allows you to drag your polygon prism around without redefining vertices. You can see how, if we move this polygon prism around a little bit, the vertex coordinates have remained unchanged. It's only the axis point that has changed. Let me move this polygon back over here. And now let's add a few vertices using the edit dialog. This plus button adds a new vertex that we can edit manually. You can see that it's just duplicated the one right before it. I'll change this coordinate to -8, and I'll leave the z coordinate at -18. So we should see a new vertex appear here once I press apply. And there it is. That's our new vertex. When you're adding new vertices this way, be aware that order matters. Vertices are connected in the order that they're listed. And we can also delete vertices from the edit dialog just by right-clicking on a row or selecting several rows at once using the Shift key and choosing delete these rows. I'll just delete this one. So what that's going to do is remove this vertex that we just created. Click apply. That vertex is gone. You can also edit a polygon prism directly from the cross section. By clicking and dragging, you can reposition existing vertices. You can add vertices by right-clicking on an edge and choosing Add Vertex here. So now I've created a vertex where I clicked on the edge there. Or you can remove an existing vertex by right-clicking on it and choosing Remove this vertex. Note that these controls are only available when your cross-section is perpendicular to your polygon prism item. So for instance, if I change the azimuth of my polygon prism item to just, let's say, 2 degrees so that it's at a skew with my cross section, and I click apply, You can still see that my polygon prism is represented here with a little skewed graphic, but those add new vertex controls, remove vertex control, those are not available. If you want those to be available, your azimuth has to line up with your cross section. And there they are again. You can see the little handles appear when those controls are available. Sometimes it can be helpful to position a vertex very far out of the cross-section frame to avoid edge effects in certain scenarios. You can do that manually with the edit dialog, or you can right-click on a vertex and choose send this vertex to the far right, or send this vertex far left. Let me do that to this vertex here. If I go to my edit dialog, I can see that indeed this vertex, its x-coordinate is now shifted to the right by 10,000 meters, which is close enough to infinite for most models. You can take a look at the infinite slab examples that come with FastGrav to get an idea of how good this approximation of an infinite point is. Let me just set this point back to something more reasonable. For some models, especially those involving infinite slabs or modeling terrain with polygons, you may wish to set your axis point to 0, 0, 0. And leave it like that for the entirety of your project creation. This effectively turns your relative vertex coordinates into absolute coordinates, which might make it easier to use real-world coordinates to construct a polygon. Check out the topography example projects that come with FastGrav to see how that is helpful. One more note about the axis point, the axis coordinate for polygon prism items. When you are hovering over your polygon prism item, you can see that this little cross is defining the axis point. So when we set this axis point, let's set it to 10, -10. You can see that that cross is located exactly at 10, -10. And if we set it to 0, 0, 0, like I was talking about before, we can see that that cross is right there at 0, 0, 0. And then by extension, if we put this vertex, or if we edit this first vertex to be at 10 meters x and 0 meters z and press apply, that vertex has a relative position of 10, 0, but also an absolute position of 10, 0 because of where this center point is. I'll end with a few miscellaneous notes about polygon prisms in FastGrav. FastGrav uses a formulation of the Talwani method to calculate a polygon's gravity effect. This method is good for any observation point, so outside of the polygon, inside of the polygon, or on a polygon's edge or vertex. So all of these results are valid. They may look funny because you've got observation stations within your polygon prism, but they are the true gravity results that you would get if you had this scenario. So you don't need to worry about your vertices being in funny positions relative to your observation points. And in fact, there are a lot of interesting situations you can mock up where the polygon vertices perfectly match the topography of your observation set. You can see that in the topography example projects. The method also assumes that your vertices are in clockwise order, looking in the direction of the azimuth vector. So that means that in the vertex list, in the edit dialog, the vertices are defined in this order. Although if you input your points in counterclockwise order, all that happens is that you get the same anomaly but negative or upside down. So just be aware of that. If you have an upside down anomaly, it's because your points are in the wrong order. The method also assumes that your vertices define a valid polygon, one that doesn't cross over itself, like this. If you have a polygon item that looks like this, these results are completely meaningless. Even though there is a graphic shown in the cross-section, this is not a real polygon, and these are not real results. These results are completely invalid. So keep that in mind. It's pretty difficult to construct a polygon on accident that looks like this. Just keep it in mind. Alright, so that's how to use polygon prisms in FastGrav. Check out the example projects and the text documentation for more info, or visit fastgrav.com or email me with questions. Thanks for watching.